All right, folks, here we are, section 6.4, continuing our study of integration. Section 6.4 is called Integration by Use Substitution. Here are the objectives we're going to look at in this section. Objective 1, use the power rule with a use substitution. 2, adjust a use substitution by a constant. I call that sometimes we have to do a little massaging. Objective 3, evaluate a definite integral by use substitution. We're going to see there are going to be two ways to do that. In objective 5, use substitution to integrate a rate function. So objective 5 is going to be, just basically an application. So folks, based on our known integration rules, if we wanted to integrate something like this, integrate the quantity x plus 2 to the 7th power dx, we would have to first expand the integrand. In other words, we would have to take x plus 2 and multiply it by itself 7 times. I don't want to do that. I don't think you want to do that either. It would most definitely take an unnecessarily long time to do. So for integrands like that, it's really written as a composition of functions. A method called use substitution, it's going to make the task much easier. So a quick for example on this integral of x plus 2 to the 7th dx. If I were to let u equal x plus 2, well, then we know the derivative of u, du dx, is 1, or in the differential notation, we'd write that as du equals dx. So differential notation, I'm going back to something that we saw, way back in chapter 3. But if I do that, if I let u equal x plus 2, then the integral x plus 2 to the 7th power dx, well, I can put u in for the x plus 2, and notice how that turns it into u to the 7th. And then I substitute in du for the dx. Now, it looks like it's going to be a lot easier to integrate u to the 7th du. In fact, we can just use the power rule, and we know the antiderivative of u to the 7th du is 1/8 u to the 8th plus c. But since we started off with x's, we have to have our answer in terms of x's. Well, we know u is x plus 2, so we do what's called back substituting. We substitute x plus 2 back in for the u, and we get a final result of 1/8 x plus 2 to the 8th power plus c. And if you go ahead and differentiate 1/8 quantity x plus 2 to the 8th plus c, if you do the derivative of that, you're going to get the original integrand. Remember, that's our built-in check, which I say here. Recall the derivative of an indefinite integral yields the integrand. So this is kind of what the power rule with use substitution would look like. You got a differentiable function of x. You let u equal f of x. Then you can write an integral of the form f of x to the n, f prime of x dx as, that mess. This is better understood simply through an example. So in this example, I'm going to show you how to use the method of use substitution to evaluate some indefinite integrals. In fact, I'm going to do 3 examples, and I'm going to have you do 2. And, here in a little bit, not quite yet, I'm going to give some general tips or guidelines on use substitution. So here are the 3 that we're going to work on right now, A, B, C. So you know the drill by now. Make sure you have these written in your notes, because I'm going to head off to the chalkboard and work out each one of them as our first 3 examples. All right, folks, here we are, the first example of showing you how the method of use substitution works. So when I look at the first one, integrate 4 quantity 4x minus 7 to the 3rd dx, the first thing I look at is what am I going to let u equal? And I'm going to start to also mention some guidelines that will come up later on, in the video. But my first thought here is I'm going to try to let u equal what's inside the parentheses. So let me write that down. U equals 4x minus 7. Okay, now this isn't an option. As soon as you write down what u is, you have to compute du, the derivative of the u statement. So the derivative, and I'm writing it in differential notation, well, the derivative of 4x minus 7 is 4, then dx. Okay, now I do the u sub. So the process of doing the u substitution, here's u. U is 4x minus 7. So I put u in for the 4x minus 7, and notice that's going to give me a u cubed. And then I look at what do I have left from the original integral? Well, here's what I have left. 4 dx. It just so happens very nicely that du is equal to 4 dx. So I'm substituting du in for 4 dx. Now we have a very, very friendly integral. I mean, this is just power rule. The antiderivative of u cubed. Well, we know that is a 1/4 u to the 4th plus c. And then my final step is something called back substitution, but I'm gonna stop saying back substitution. My final step is to replace the u. I mean, my problem started off with x's, my answer needs to have x's. So since u was 4x minus 7, I'm going to put 4x minus 7 back in here for u, and I get 1/4 4x minus 7 to the 4th plus c. One more time, how do I know this is really the correct antiderivative? That's right, differentiate this. When I differentiate this, I better get the original integrand back. All right, let's look at the one in part B. So in part B, let's see, we are asked to integrate 1/2 square root x plus 9 over 2 dx. All right, so here I will start off by letting u equal what's under the radical sign. That's kind of the same thing as saying let u equal what's inside the parentheses. So I'm going to let u equal x plus 9 over 2. Now keep in mind x plus 9 over 2. That's really just the same thing as 1/2 x plus 9/2. Now it's not an option. I have to compute the derivative. du, and it's easier for me to do the derivative of when it's written like this. So the derivative is just 1/2 dx. Alright, so now I go through the process of substituting. So I substitute, I always do my u sub first. So u is x plus 9 over 2, so there's u. So I have square root u, and then I look at the original integral and see what do I still have left. Well, I have a 1/2 dx. Well, 1/2 dx is du. So I'm substituting du in for the 1/2 dx. And, well, my next step is to rewrite the radical as u to the 1/2 power. And then get an antiderivative. Remember, I'm going to add 1 to the exponent. The little multiplier in front's the reciprocal of the new exponent. And then I resubstitute. My u was x plus 9 over 2, so I put x plus 9 over 2 back in here for u. And that's the antiderivative of that integral. One more time, you can check this by differentiating. and you will get the original integrand. There was a part C, so let me put part C up here. I'm going to erase part A. Part C was integrating the fourth root of x squared plus 9x times 2x plus 9 dx. Wow. My first thought is I'm going to try to let u equal the radicand, or what's under the radical sign. This is what I'm going to let u equal. So u is x squared plus 9x. Now I have to immediately compute the derivative of u. This isn't an option. You must always do this. So the derivative of u, du, is 2x plus 9 dx. So now I go through the process of substitution. I always do my u sub first. So u is x squared plus 9x. So this is u. So I'd have the fourth root of u. And now I look at what do I still have left from the original problem. Well, I have 2x plus 9 dx. du is equal to 2x plus 9 dx. So I'm going to substitute du for the 2x plus 9 dx. And we're almost there. Rewrite the fourth root of u as u to the 1/4 power. Then you use your power rule, so you add 1 to the exponent. Put the reciprocal out front as a little multiplier. Then resubstitute. So you get 4/5. Okay, there's my u. X squared plus 9x to the 5/4 power plus c. Okay, so there's 3 examples of the basics of u sub. So what I'd like you to try right now in section 6.4, I'd like you to do number 10 and number 12. So you know the drill by now. Pause the video, do number 10, do number 12. Once you've done those 2, restart the video and I'll be here at the chalkboard working out the solution to them, and hopefully you'll get them both correct. Alright folks, here we go with number 10. Number 10, you were asked to integrate 6x times the quantity 3x squared minus 5 to the 3rd power dx. So I'd start off by letting u equal what's inside the parentheses, 3x squared minus 5. Then I compute the derivative. So du, the derivative, is 6x dx. Then I substitute in. I always do my u sub first. So here's u. So I have u to the 3rd power. And then what do I have left? Well, I still have a 6x dx. Well, 6x dx is exactly equal to du, so I substitute the du in. Get my antiderivative, 1/4 u to the 4th plus c. Then resubstitute my u, and I get the antiderivative to be 1/4 3x squared minus 5 to the 4th power plus c. So that's the antiderivative. All right, number 12. You were asked to integrate 10x cube root 5x squared minus 11 dx. So I would start off here. I'm going to go ahead and let u equal what's under the radical sign. 5x squared minus 11. Then I have to compute the derivative, du. So du is 10x dx. Now I substitute. So when I substitute, I always do my u sub first. So u is 5x squared minus 11. There's u. 5x squared minus 11. So when I substitute u in there, I'm going to have the cube root of u. And then I look at what do I have left to take care of. Well, I have a 10x dx still left over to take care of. Well, 10x dx is exactly equal to du, so I substitute du in for the 10x dx. And I'm almost there. I have to rewrite cube root of u as u to the 1/3. Use my power rule, so I add 1 to the exponent. Put the reciprocal of the new exponent out front as a little multiplier. And then don't forget to resubstitute to get back to x's. So we have a 3/4 5x squared minus 11 to the 4/3 power plus c. And that's the antiderivative. Okay, you may have noticed in the first 3 examples I did, and these 2 homework problems that you practiced and hopefully you got correct, you may have noticed that for all 5 of those we've done so far, our du statement has just perfectly matched the remainder of the integrand. For example, here, du is 6x dx, and that just perfectly matched 6x dx. That's not always going to be the case, so let's head on back to the slides to discuss what we're going to do when that happens. All right, after doing those 3 examples, and hopefully you were able to do numbers 10 and 12, we're going to move on, because not always does our u substitution initially work. You may have noticed in the first 3 examples and in numbers 10 and 12, we let u equal something, and du happened to match perfectly the rest of the integrand. Well, quite often it might be necessary to multiply or divide by a constant in order to match the remaining part of the integrand. This is what I call massaging the du statement. So to show you how this works, I think it's best handled through an example. So we're going to evaluate this integral, x square root 8x squared plus 9 dx. And then I'll have you practice a couple of them. But this example, I'm going to show you how we massage the du statement. So again, you know the drill. Make sure you have this written down because I'm going to head off to the chalkboard to do this example. All right, in this example, we were asked to integrate x square root 8x squared plus 9. I have an extra x in there. 8x squared plus 9 is under the radical dx. So I'm going to begin like I've started off all the other problems so far. I'm going to let u equal what's under the radical sign. So u equals 8x squared plus 9. And like I've done every time so far, and I've stressed, I must compute the derivative of my u statement. So I have to get the derivative here. du is 16x dx. All right, so I do the u sub. I always take care of my u first. So here's u. So I'm going to have square root of u. And now I look at what I have left. I have an x dx that's left over. Does du equal x dx? No, it doesn't. Du equals 16x dx. So I have to come into my du statement and I have to do a little bit of massaging to it. In order to see an x dx over here, this is an equation. I can treat it as an equation. I can divide both sides of that equation by 16 to get an x dx. And if I divide both sides by 16, I'm going to write it as a 1/16 du. So what do I have left over? I had an x dx. What does x dx equal? Well, x dx equals 1/16 du. That's what I need to substitute in for x dx, 1/16 du. So let me go ahead and do it this way, a 1/16 du. The next thing I would do, and I would immediately do it, 1/16 is a constant. So let's rip that out front of the integral sign. So we have a 1/16 the integral. And I'm also going to go ahead and rewrite the square root of u at this step as u to the 1/2. And now it's just a matter of, well, it's a Nike problem. Just do it. The antiderivative is 1/16. Make a set of parentheses. Use the power rule on u to the 1/2. So I would add 1 to the exponent. So 1/2 plus 1 is 3/2. The little multiplier I put in here is the reciprocal of the new exponent. Tack on my plus c. And I'm almost done. Not quite. By the way, what's 1/16 times 2/3? That's right, it's 1/24. Resubstitute my u statement. So I put x squared plus 9 back in here for u. And there we have it. So this is an example of what's going to happen frequently. You have to massage the du statement. So to make sure you're getting an idea of how to do this, I have a couple I'd like you to do here in section 6.4. Go ahead and do numbers 22 and 26. So as always, pause the video, do those two. Once you've completed those two, restart the video and I'll be here at the board working them out. Alright folks, number 22, you were asked to integrate an x squared times the quantity x cubed minus 1 to the 3rd power dx. So hopefully you knew right away to let u equal x cubed minus 1. du is 3x squared dx. du is always the derivative of your u statement. So when you substitute in, take care of the u first. So you have a u cubed. And then when I look at what I have left over, I still have an x squared dx. du equals 3x squared dx. That means, dividing both sides by 3, a 1/3 du is x squared dx. So for the x squared dx, I'm going to substitute in 1/3 du for x squared dx. And as soon as I substitute in the 1/3 du, I would take that 1/3 and rip it out front. So I'm just going to do that at this time. Now it's just a Nike problem. Just do it. Antiderivative, 1/3. Leave a space. u, my new exponent, add 1 is a 4. And here I put the reciprocal of the new exponent. See, 1/3 times 1/4 is a 1/12. Resubstitute for the u. So u is x cubed minus 1. And that is it. Number 26. Well, number 26, I would start off by letting u equal what's inside the parentheses in the denominator. So u is a 3x cubed minus 8. du, the derivative of the u statement, is 24x squared dx. So here I go substituting. Remember, I always take care of my u sub first. So here's u, so my denominator is u to the 5th. And then I look at what do I still have to take care of after I do that u sub. Well, what I have to take care of is x squared dx. So looking at my du statement, it looks like a 1/24 is equal to an x squared dx. So I'm substituting 1/24, whoops, du. Sorry, I forgot my du there. I'm substituting a 1/24 du for the x squared dx. So as soon as I put in here 1/24 du, that 1/24, well, I'd rip it out front. Just leave me with a 1 in the numerator. And then one little step of algebra. Rewrite 1 over u to the 5th as u to the negative 5th. Now has me prepped to use the power rule. So let's see, I add 1 to the exponent, so that gives me a -4. And here goes the reciprocal of the new exponent, and that's a -1/4. Tack on a plus c. And see, if I multiply these two together, I get a -1 over 96, I believe. Resubstitute the u, so here's the u. 3x cubed minus 8 to the -4th power plus c. And if you wanted to, you could write this as -1 over 96 quantity 3x cubed minus 8 to the 4th power. So you could rewrite the negative exponent, making it a positive exponent. But I ran out of room, so I'm not going to do that, and I'm going to stop right here. So hopefully you're seeing how to handle a u sub when you have to kind of massage the du statement. So let's head back to the slides and see what's next. All right, so now to kind of formalize things on guidelines or tips on u substitution. As you know, you've already heard and maybe surmised, you know, generally speaking, the correct choice for u, what you're going to let u equal, it's usually going to be a radicand. That's a fancy way of saying stuff that's under a radical sign. It could be what you see in the denominator. It could be what you see in parentheses. Or, you know, I could add to this, it could be what you see in the exponent position. Now, stuff in the denominator or in an exponent position, you won't see that come out until section 6.5, the next section. But generally speaking, try to let u equal what's inside parentheses, under a radical, in the denominator, or if it's a function in the exponent position. And denominator and exponents, you'll see that in section 6.5. So once you write down what you think u is, you must compute du. That's the derivative of your u statement. And du equals whatever you're saying u is. It's, you know, the derivative. And there's a typo right here. That should say dx. I'll make a call out for that. But du is equal to f prime of x dx. Sometimes you have to multiply or divide du by a constant to make the remaining part of the integral, you know, match the differential in u, to match your statement, as you've seen. Then after you do the u substitution, so you know you substitute your u in, you substitute in your du, you should have nothing in the problem that contains an x. Everything should be in terms of u. And then it's a Nike problem. Just do it. Integrate with respect to u, back substitute, so you can rewrite the integral in terms of the original independent variable, you know, which is usually x. All right, now we're getting ready to look at how do we attack definite integrals when we've done a u substitution. And there are two ways to do this. So way one, or route one, Write down what you think your u sub is. Do your u sub. Perform the integration with respect to du. And then back substitute, rewrite the answer in terms of x. Then you can evaluate the definite integral using the original limits of integration. Route 2, you're going to do your u sub. You're going to rewrite the integral, the integrand in terms of u, but you're going to rewrite the original limits of integration in terms of the variable u. So you're going to turn them into u limits. You integrate, get your antiderivative in terms of u, and just evaluate it using the u limits of integration. Either route you go, you're going to get the same answer. You know, I don't care which route you use, but in this first example, I'm going to do this first example both ways, route 1 and route 2, to show you we get the same answer, and then I'm not going to care which route you decide you want to use to evaluate a definite integral when a u substitution is taking place. So make sure you write this down because now I'm going to head off to the chalkboard and I'm going to show you both ways to do this problem. All right, folks, in this example, we're going to evaluate a definite integral where the definite integral requires u substitution. And remember I said in the slides there are going to be two routes you could go on how to do this evaluation. It doesn't matter which route you take, you're going to get the same answer. And I don't care which route you use. You use whichever route you are most comfortable with. So let me go through the two different routes. So here's route 1. So let me write it down. Both routes are going to have the same initial step. You're going to do a u substitution. So u is x squared plus 4. du is 2x dx. So we know when we do the u substitution, take care of the u first. So here's u. So I have a u cubed. Oh, this works out nicely. 2x dx is exactly equal to du, so I don't have to do any massaging. And that's all I write down now on route 1. I leave off those limits of integration on route 1, and that's because these limits of integration, they belong to the variable x. It's actually shorthand notation. This is shorthand notation for x equals 0. This means x equals 2. It's for the variable x, not the variable u. So I leave off the limits, do the calculus, get an antiderivative. Antiderivative is 1/4 u to the 4th. Resubstitute. So put that back in for u. And now I bring back the limits of integration because I have my antiderivative in terms of x, so I can use the x limits. And now I crank this through the fundamental theorem of calculus, so you know the 2 goes in, minus, then putting the 0 in, and you should end up with 960. All right, so route 2. Let me write down the problem again. So route 2 has the exact same starting point. We're going to do a u sub. So we let u equal x squared plus 4. du is equal to 2x dx. Substitute. So I do my u first. So I have a u cubed. 2x dx is still du. I mean, everything's looking the same, but here's where it differs. I'm going to change these x limits. I'm going to change them into u limits. And here's how I change them into u limits. This says x equals 0. So if x equals 0, put 0 in here for x. And you would get u equals 4. This says x equals 2. Put 2 in here for x. and you end up getting u equals 8, because 2 squared plus 4 is 8. So I've changed those x limits, I've changed them into u limits. Integrate, and we get an antiderivative of 1/4 u to the 4th, and now I can use those u limits with the fundamental theorem of calculus. I mean, it's a 1/4 8 to the 4th power minus 1/4 4 to the 4th power, and I'm going to still get 960. Okay, so folks, those are the two different routes you can go. I don't care which route you go. It doesn't matter. You get the same answer. You do the route that makes the most sense to you. So in the homework, I think there's a block of exercises where in the block of exercises they say, it's said in the directions, do not change the limits of integration. And then there's another block of exercises that says in the directions, change to u limits. So the directions are basically saying for one block, do route 1. For the other block, do route 2. So let me just change all of those directions. I don't care which method you use. Use one method or the other. I don't care. Do whichever method you are most happy with. Okay, so that's it for this one. Let's head back to the slides and see what we have left in this section. All right, now that you've seen how to evaluate a definite integral that involves a u substitution, and there are two ways to do it, let's conclude the section by looking at integrating a rate function that requires a u substitution. So for this example, I thought what we would do is number 71 on page 471. So make sure you have your book, get your book open, page 471, number 71. This is a marginal profit function, and I believe this example has, or this exercise has 3 parts to it. So we'll do all 3 parts. So I'm heading off to the chalkboard to do number 71 on page 471. All right, folks, this example, it's an application. I said we'd just do number 71 from the book. So hopefully you have the book. You're looking at number 71. I'm not going to read it to you because it's right there in front of you. I just wrote down the important stuff. This is the marginal profit function we were given. We were told X represents the number of flags, and the marginal profit itself was measured in hundreds of dollars. So in part A, we were asked to pretty much evaluate the marginal profit at 70, when 70 flags are being produced and sold. So when we toss 70 in there, when we evaluate marginal profit at 70, so 70 comes in here for X, 70 comes in here for X. I mean, I used my calculator, and I got MP of 70 to be a 1.44. I didn't say anything about absolutely having to interpret it. I'm going to interpret this anyways. This just simply means that when this company produces and sells the 71st flag, the additional profit would be, well, about $144. How do I know 144 and not $1.44? Well, MP is in hundreds. But it was just simply to evaluate them and get the marginal profit. So I'm moving on to part B. Part B, integrate from 20 to 100 the marginal profit function. So integrate from 20 to 100 the marginal profit function. Well, first things first. We are integrating a rate function. When you integrate a rate function, it gives you a total accumulation. It gives either a total increase or a total decrease. Increase if you have a positive number, decrease if you have a negative number. So I'm kind of thinking that integrating this rate function from 20 to 100 is going to tell me like a total increase or a total decrease in profit from selling 20 to 100 of these flags. Let's get on with it. We have to do a u sub. So I'd let u equal the 2x squared minus 400. du is a 4x dx. So when I substitute in, well, in the denominator I have the square root of u. I still have a 2x dx to take care of. Well, it looks like it's almost, I have a 4x dx here. Well, if I just divide by 2, 1/2 du would be a 2x dx. So I substitute in 1/2 du for the 2x dx. So 1/2 du, I'll rip the 1/2 out front. And then this is the decision. Route 1, because it's a definite integral. Do we go route 1 or do we go route 2? It doesn't matter. So I'm going to go route 1. I'm going to leave off the limits of integration. And let's see, I get a 1/2. I have to rewrite that. That's u to the negative 1/2 du. And then when I get my antiderivative, I should get a 1/2. Let's see, this would be u to the 1/2. I'd have a 2 in there. So 1/2 times 2 is 1. Substituting back my u, so I'd have a 2x squared minus 400 to the 1/2 power. Bring back the original limits of integration. And keep in mind, the 1/2 power, I'm going to rewrite this one more time. That's a square root of 2x squared minus 400. And then when I crank this through the fundamental theorem of calculus, I'm going to end up getting 120. So let's verbalize the interpretation. Not going to write it down. You know, you can pause and rewind the video as often as necessary to get the interpretation down. Here's what that 120 means. The total increase in profit for producing and selling 20 to 100 flags is $12,000. Keep in mind, this is in hundreds. It told us at the beginning, it's in hundreds. So that would be the interpretation. Okay, part C is a really old problem. Part C, recover the profit function. You were given profit is 0 when x is 20. So we know to recover a profit function, we have to integrate marginal profit. All right, folks, now look, we've already done the antiderivative of marginal profit. We integrated this, and we came up with this as being the antiderivative of marginal profit. I'm not going to go through all that work again. I've already done it. So I have square root of 2x squared minus 400 plus c. It's an indefinite integral, so there would be a plus c. Now we need to figure out that constant of integration. Well, we were given profit is 0 when x is 20. That means when 20 goes in for the x, when we put 20 in for the x, the result has to be, that's a 0. The result has to be 0. Well, if you take the square root of 2 times 20 squared minus 400, if you do the square root of all that stuff, you get 20. Subtract 20 from both sides, you get c is negative 20. So that means the profit function is the square root of 2x squared minus 400 minus 20. So that's all three parts for number 71. Hopefully you're feeling kind of comfortable with this. This ends the section. This ends the material. So now you're ready. You can head off and do the homework that's assigned in section 6.4. Thanks for watching.